So hello, welcome to another practice problem solving day for Physics 2. Today we're going to be looking at problems from chapter 21. Hopefully some of you at least glanced at the packet since it's up there. But we're going to be doing a series of problems that this chapter, it's going to have a good spread of problems. Because we talked about electric potential difference, commonly called voltage. We also talked about electrical potential energy, and we also talked about capacitors. And so I'm going to do problems that kind of cover both those ideas, or all of those ideas, which is why I have scattered throughout the screen multiple things showing the topics, with potential energy and voltage in the upper left, and everything capacitor in the bottom right. And I'm going to jump straight into this first problem. Like always, interrupt me if you need for any point. And the first problem is, the three charges in the attached figure are at verticals of an isosceles triangle. Let Q equal 7 nanocoulombs and calculate the electrical potential difference at the midpoint of the base. Now, I already drew this. What we know is that this whole thing across is 2 centimeters. That means the distance from either of these negatives to the midpoint of the base is 1 centimeter, or 0.01 meter. We also know this height is 4 centimeters, or 0.04 meters. Now, if I want to find the potential, yeah, I'm gonna have that off. If I want to find the potential is given as KEQ over R. And potential is not a vector, so I'm just going to find it for each one and add it up. Now, I'm then going to need to find the potential for each guy. That means I need all for each one. Now, this problem doesn't number them, but I'm going to number these just to make it easier to solve. Well, I'm going to call this Q1, this guy Q2, and this guy Q3. And you know what, let's just get rid of these negative signs because I'm just going to call them that. Well, Q1 equals negative Q2 equals negative Q3. So I'm going to start by saying some of the distances, right? We know R2 and R3 is 0.01 meters. For R1, the distance from here to this guy, I'm going to have to solve for that. But I can just say, you know what? This is 4 centimeters. This is 1 centimeter. What's this guy? Pythagorean theorem. That 0.04 squared equals 0.01 squared plus all 1 squared. That means 0.04 meters squared minus 0.01 meters squared equals R1 squared. And I'm already going off the bottom. I'll just write that again right ahead up there. And I'm going to skip me doing that algebra and just say that means R1 is 0.03873 meters. You can do that math yourself if you need. Now, when last chapter, when we did electric field and forces, this all became a mess because of vectors, right? If I wanted the electric field at this point, I'd have to be like, okay, Q2 points to the left, Q3 points to the right, Q1 points up. But for potential, it is not a vector. Potential is a scalar, which means I can just shove in. The total potential is just going to be V1 plus V2 plus V3, or KE Q1 over R1 plus KE Q2 over R2 plus KE Q3 over R3. Now, in my solutions, I kind of factored this out in a weird way, but I'll be nice and not do that here and say that means it is 8.9, no, just for space. For space, I'll factor it out. Keep in mind that Q1 equals negative Q2 equals negative Q3. So I'm going to say this is the same as KE Q over R1 plus KE negative Q over R2 plus KE negative Q over R3. Just because that's the values, right? Q, negative Q, negative Q. And I'm just going to factor out my KEs and Qs. 1 over R1 minus 1 over R2 minus 1 over R3. Now, when we did forces and electric field, I had an absolute value because we only cared about direction. Here, you do not want to do that. I have to mark this as a negative Q and a negative Q. But otherwise, this is 8.99 times 10 to the 9th Newton meters per, that's not the right units. Newtons meters squared per Coulomb squared. Q in this case was 7 nanocoulombs. R1, I said, was 0.03873. R2 was 0.01 meters, and R3 was 0.01 meters. These two numbers multiplied together, 8.99 E9 and 7 E negative 9, ends up being 62.9125. And everything in here, this minus that, ends up being a negative 174.18 inverse meters. And I can get my answer. Potential, or electric potential difference, to be more precise, let's move the mouse out of my forehead. Electric potential or electric potential difference is so much easier than force and energy because we do not have to do vectors. I simply say, what's the potential from this guy? What's the potential from that guy? What's the potential from the third one? And add them up. No vectors needed. And that's it. It's actually kind of straightforward. Any questions? Okay. I'll jump to the next one. This next one, which is a two-podal, is using the same kind of logic. And it says we have 2-point charges. Q equals 5 and Q equals negative 3. And I'm going to just, because I always do, I'm going to number them. So I'm going to say Q1 equals 5 nanocoulombs. Q2 equals negative 3 nanocoulombs. And I'm going to say these two charges, they're separated by 35 centimeters. And they ask, what is the electric potential difference at the middle? Now, if I want to find that electric potential difference, if this whole thing is 0.35 meters, I can say from here to there is 0.175 meters. Right? If I want to find the electric potential at that point, then it's going to be the same thing. That V is going to just be V1 plus V2. Or KEQ1 over R1 plus KEQ2 over R2, which is going to be 8.99 times 10 to the 9th Newton meters squared per Coulomb squared Q1, 5 times 10 negative 9 coulombs over 0.175 meters, plus 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, negative 3 times 10 negative 9 over 0.175 meters. I don't know why I didn't factor it out this time. In the solution I did. And get a value. Pretty straightforward. Part B says what's the potential energy of the pair of charges? Well, now I got to use a different equation because now I'm looking for potential energy. And there is a relationship between potential energy and potential, except that is assuming you have some other charge going. If I want the potential energy of the pair of charges, I'm just going to go straight to my potential energy equation. Well, potential energy is Ke, that's an E, Q1, Q2 over all. Now note, it doesn't say what's the potential energy at the midpoint. It says what's the potential energy from these charges. And so if I just stick to the same thing, 8.99 times 10 to the ninth, and then we have 5 times 10 negative 9 times negative 3 times 10 negative 9. My all is going to be the distance between them because that will give us the potential energy of the pair. I'm going to use my 0.35 meters. I don't use the 0.175 because nowhere in this part does it say anything about the halfway point. Well, if I want the potential at the halfway point, then I use that. But if I want, and see, you got to be careful here because I say the potential at the halfway point, I'm talking voltage. But if I say the potential energy, well, suddenly it's energy. And therefore, I'm not saying what is the potential energy at the midpoint. I'm just saying what's the potential energy of these charges. And so I have to go and use the whole distance. Now I can do that math. And get this value. So this is a textbook problem. So as a textbook problem, it asks some weird questions. And what it says is, what is the significance of the algebraic sign of your answer? That's the kind of thing I probably would never have you do on an exam, but it's good to think about. This potential energy is negative. So what that means, if it's negative, well, let's think about potential energy to gravity when it's negative, right? If I define my zeros here, anything raised up has potential energy. Anything beneath has negative potential energy. Negative potential energy, what it means is that it's kind of wanted to go that way. Like that's what it would have naturally done. When you have a negative potential energy, that means it will be harder to separate the particles. And that if you, what it is that if these particles are going to try to come together, and if you want to keep them apart, it's going to take work. That's what the negative means. The negative means that they want to come together. Questions?
So anytime I get an answer with a negative like this, that means my particles are attracted to one another.
It does. Yep. Which makes sense because the only way to get a negative is to multiply a positive and a negative, right? If it's a positive and positive, you get positive. If it's negative and negative, you get positive also. It's when they're positive and negative, they want to come together.
Okay.
Okay. Okay.
Lars?
Yeah.
Sorry, my mic wasn't working for a second. Could you give a question like on a negative? Could you word it to be something like you give us distance Q1, Q2, and could you say you give us E? Could you say like find the work between these 2 point charges as they're trying to come together?
I mean, yeah, I could say that I probably won't. That really it's going from work to potential energy. That's much more heavily a physics 1 thing for me to really hit up again. I try not to be like, hi, you remember this stuff? Although I did cover that again. If I asked for the work to do it, work would be the negative change in potential energy. And so therefore to bring these together, well, sorry, to depends what you want to do. Work is negative change in potential energy, right?
Yeah.
So I could say if these came out from infinity, how much work would it take to do it? But that doesn't even really make sense either. But if I did, you get that it would take negative 3.85 because final minus initial. I'd have to give 2 cases. If I asked for work, I'd say here's a situation, and then I'd probably do another one and be like, okay, now this particle is here, and these fall apart. Find the potential energy. Okay, what's the work? Like if I ask for work, it's going to be you do the energy at 2 different spots and subtract them.
Okay.
I don't think I did that on the homework. I might have. I have to remember, but I'm pretty sure I didn't. Now, that's potential energy and voltage. I mean, it's really potential energy and voltage really aren't that complicated because it's just you plug and chug into those. Let me grab this. It's just you plug and chug into these equations. That's all it is. Last semester, I did not put a problem on the exam about those, in fact. I figured that dealing with forces and electric fields is HODL, so I could just stick to those. Because the rest of the chapter is about capacitors. So I'm going to jump into this next one that says, a parallel plate capacitor with an area, okay, let's just start writing things down. With an area of 0.2 meters squared and a plate separation of 3 millimeters, or 3 times 10 negative 3 meters, is connected to a 6-volt battery. What is the capacitance? Okay, I gave the area and the distance between the plates for a parallel plate capacitor. On the over here, this thing that I'm moving around, I give the equation for the capacitance. Capacitance is given as the permittivity of free space times the area over the distance. Now the permittivity of free space, which is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared, times the area over the distance. And I mean, that's just kind of plug and chug. It's 5.9 times 10 to the negative 10. That would end up being a Coulomb squared meter per Newton, but that's the same as a farad. B, how much charge is stored on the plates? Well, charge, Q equals CV. So it's just the value we got, 5.9 times 10. Did I just put 5.9? Did I not put another digit? I didn't. That was bad of me. 5.9 times 10 to the negative 10 farads times 6 volts. Must have been 5.9 now. I'm betting. And it's just I messed up and didn't put the other sig fig. 3.54 times 10 to the negative 9 coulombs. And C, which I'm putting over here because I can work it logically on a piece of paper. Oh, sorry. C, what's the electric field between the plates? Now, that equation is not up here on any of the things I grabbed. I apologize for that. It was in the notes, though. In the notes, I said that the electric field between the plates of a capacitor went by voltage over distance between them. Sorry I didn't make that pop up. Well, it kind of is. It's similar to, it really comes out of this one right here. We're just off by a negative sign because we're taking the infinity to be 0. But I derived this equation directly, this E equals V over D, that I just did. I gave this explicitly in the notes. I just literally forgot to grab it when I set up the slides for put on the screen for this. And so it'll just be 6 volts over 3 times 10 negative 3 meters, which is 2,000. And D is how much energy is stored in the capacitor, which is given as U. U is well, that's a lot of equations for U. I only gave one though, but U is 1/2 CV squared is the quick one. I could also say that U is 1/2 QV. That's a Q, not a G. I could also say U is Q squared over 2C. But let's just stick to 1/2 CV squared. 1/2 C times V squared. Really, that's a plug and chug problem. That's way too simple for me to put in an exam. Questions though? Okay. Let's do an actual difficult one then. And this one is the one that's most similar to what was on the exam last semester. Yep. I just have a box of crumpled up paper over there. Okay. Find the top, find the top. What this one says is, hey, I got this set up. Find the equivalent capacitance plus the charge on each capacitor plus the voltage on each capacitor. And I'm going to stick to the same color coding the problem does. Now, it doesn't number them. It just says, hey, look, they have these values. I'm going to number them for solving. And I am going to pretty arbitrarily call them C1, C2, C3, and C4. Now, I talked about when I did this in class in the notes that I say always keep all your drawings. You actually get to see me do it this way for the first time today. So I'm going to go through and say, okay, C1 in series goes to this mess, which in series goes to C4. This mess right here is the first thing I got to take care of because it's its own little fusion. So, and I'm going to stop color coding all the things it's annoying. So I can say this would be the same as this, where the capacitor up top is a C23. But the capacitor at the top is just a combination of C2 and C3. But C2 and C3 are in parallel. So C23 is made up of, once again, capacitors 2 and 3 in parallel. And as I have over here, in parallel, they just add up. So this is going to be the same as C2 plus C3, or 6 microfarads, and what, 2 microfarads? And 2 microfarads, which is 8 microfarads. So C23 is 8 microfarads. Once I do that, I now have 3 capacitors in series. If I have 3 capacitors in series, I can say, okay, it's just 3 in series. I can make one equivalent capacitor. How low can I go? That's good. I gotta be careful. When I draw them, my batteries and capacitors sometimes look the same. That's why I normally try to color code things. But I can say this could be just as one capacitor, a C1234, where C1234 is made up of 3 capacitors that were in series. Yes, one of those capacitors isn't really a capacitor, it's 2 shoved together, but this drawing has 3, so I'm treating it as 3. Now, I'm going to actually just call this C equivalent in the end, because that's what I'm looking for, the equivalent capacitance of the entire circuit. And I can't, but because they're in series, what I have to say is 1 over C equivalent is 1 over C1 plus 1 over C23 plus 1 over C4. Which is 1 over 8. Oh, wait, they are 8? Yeah, okay, 1 over 8 microfarads plus 1 over 8 microfarads plus 1 over 8 microfarads, which is 3 over 8 microfarads. But that's not C equivalent, that's 1 over C equivalent. So C equivalent is then 8 microfarads over 3, which is 2.67. There's my answer to Pode. Any questions there?
Nope, I got it.
Okay. So what I can do is if I know the C equivalent, I know the voltage equivalent is going to be whatever the voltage of that battery is. That was a 9-volt battery, so that's V equivalent. Because that's the only thing that's hooked up to it. The battery, all of its potential is going to that capacitor. I could also find Q equivalent, because Q equals CV. So Q equivalent will just be 2.67 times 10 to the negative 6 farads times the voltage, 9 volts. So Q equivalent is 2.4. Oh yeah, it's actually 2.40. It's 2.40 times 10 to the negative 5th coulombs. But once again, this guy doesn't really exist. This is really made up of 3 capacitors in series. But I can look, 3 capacitors in series. In series, let's get my pen again. In series, Q equivalent equals Q1 equals Q2 equals Q3 and so on. Which means if that's my Q equivalent, let's focus that kernel. That means, and I'm going to work my way back up, Q1 equals Q23 equals Q4 equals 2.40 times 10 negative 5th coulombs. I now know the charge on 1 and 4. I did say what's the charge on each one, what's the potential difference on each one. If I want to get the potential difference on each one, Q equals CV, means that V equals Q over C. And so V1 is Q1 over C1. That was 8 microfarads. Three volts. Q4, I'm going to jump straight to that one. Or V4, I mean. V4 is, well, by luck, they gave the same value capacitance for both. So that wouldn't normally be true, that the voltages are the same, but Qs would definitely be the same, and they just were both 8 microfarad capacitors. And actually, that guy was 8 microfarads too. So that's also V23. That in this case, all of them have the same voltage also, because all of them have the same capacitance. That's just a nice little step that wouldn't normally be true. But now I can say, okay, this guy has a 3 volts over it. But this is made up of 2 capacitors in parallel. And in parallel, that means voltage 2, 3, because they're in parallel is the same as voltage of 2, same as voltage of 3. So V2 is 3 volts, and V3 is 3 volts. And I can get the charge on each one by saying Q2 equals C2V2, or 6 microfarads times 3, or 18 times 10 to the negative 6 coulombs, which I know that's not really the most proper scientific notation, but I'm just doing it in my head. And Q3 is C3V3, or 2. Wait, what's the value for that one? Let's scroll over 2. 2 times 10 negative 6 farads times 3 volts equals 6 times 10 negative 6 coulombs. And there I go. Q1, Q2, Q3, Q4. Meanwhile, V1, V2, V3, V4, all of them have 3 volts. Questions? Okay, the next one, which is basically the same thing, but more complicated. And it says, hey, look at this complicated mess. Find the equivalent capacitance. Let's pretend it was hooked up to a battery. If it was hooked up to a battery, what's the voltage and charge on each one? And it'll be the same thing. You'll work your way down the sheet, then work your way back up. I always like to not make these example problem days go past the 25 minutes, which I've already passed, just because that's how long I would have spent in lecture if we were in person, because you would have worked on them for half an hour. And I'm still going on the assumption that you guys are working on them on your own, which I know nobody is, but I'm pretending you all for my own sanity ahead of time. So I don't want to take extra time in class. So I will stop there. But this will be the same idea, where you'll work the capacitors and start from a complicated to make it more and more and more simple, and then work your way back up. Any questions on those?
Yeah, just on number 3.
On 3.
Yeah, back to
This guy?
no, the 4, my bad. 4.
Okay.
Yeah, on 4. So this condition that you said where it was all 3 volts.
Yep.
I'm not really understanding
Oh,
that
why they were all
specific
3
condition.
volts?
Yeah.
Okay.
Yeah.
The reason why, I'm going to get rid of the top one for a second, right, is that I should find the voltage differently, right? So V1 should be Q equals CV. Sorry. V1 should be Q1 over C1, right? V23 is Q23 over C23. And V4 is Q4 over C4, right? Now, because they're in series, all of these Qs are the same. Follow so far?
Yes.
Because of coincidence and luck, look at the capacitances. That the capacitance of each one, this guy is 8, this guy is 8, and when these two added together, they were 8.
Oh, okay.
They were all the
Okay.
same just because it happened to be, and I didn't even realize that at first. That's why I started writing V1, and then I'm like, oh wait, shit, V4 is also 8. Oh wait, V23 is also
Yeah.
8. It's just because they happen to all have the same numbers. It's a way, I guess, to make the problem a little simpler.
And that 9 volts, that's different. Why?
The
Why
9
is
volts.
this?
That was the battery.
That's yes, that's the bad. Okay, I see.
And that's spread out. So
Clumps together. So
3 of the
the three,
volts. Sorry, say it again.
and the three volt charges sum together to make the 9 volt, right?
Yep, exactly. Because you get 3 here, 3 here, and the other 3 is here.
Okay.
So they 3, 3, 3, 3, 9.
And that could be sort of like a way to check it. Sort of, you got like
Yeah.
3 volts and stuff. Yeah.
Things in series, the voltages will add up. You got to be careful because it's weird because you say those 4 capacitors each have 3 volts, you get 9, and at first it's like that doesn't make sense. If it's 3 each with 3, that should be 12. But it's because when you're in parallel that it shares it. We have 3 things in series, each with 3. There's 9.
Okay.
Oh, good timing. My headphones just started beeping saying the battery's about to die. But we're ending anyways. Any other questions?
Oh, I think I'm good.
All right. Well, I'm going to stop recording in a second then. Have a good weekend. You got nothing for a little while. Labs were but they all graded. Homework was pretty bad. Get help for homework as needed. Other than that,